So in this video, I want to go over fixed and random effects again. We talked about them earlier in the semester, but this is more of a comprehensive looking across different kinds of models to make decisions about fixed and random effects and be smart about it. I will be talking about three different examples, and one is cross-sectional data, and then I have two longitudinal examples that have somewhat different research questions, somewhat different modeling. So the first one is cross-sectional data, and the research question that I want to model is, does walking in your neighborhood depend on dog ownership? And then I have a possible follow-up question. Does the relationship between dog ownership and walking depend on the presence of sidewalks in your neighborhood? And as you can see on the right-hand side, this is a very simple model. The first, the green arrow demonstrating what would be modeled to answer the research question, and then the blue arrow adding a moderator that is a neighborhood predictor to that situation. So in terms of walking, you can think about this outcome as a dichotomous outcome. Do you walk in your neighborhood, yes or no? Or you can have it as a continuous outcome. How much time do you spend a week walking your neighborhood? To make this really focused on the random and fixed effects, I chose to just go with continuous outcomes, but things would just look exactly the same except for a different link function. So the unconditional model is a random intercepts model, as you well know. And so you have your level 1 equation where you have your outcome and you have your intercept. And then your intercept gets modeled as a grand mean and some neighborhood random effect. So here I have an overview slide of what happens if we're adding dog ownership. I want to focus on level 1. So we're adding a term on level 1. It's beta 1j times dog ij. So it's that's what we're adding to level 1, and that does not change whether we add a random or fixed effect, because the question is, how are we going to model beta 1j? So this is the big question if we're asking the question, should we model dog ownership as a random or fixed effect? And I'm going to walk through those four examples that I show you in terms of making decisions. And so what you can see is that we have four different ways of modeling beta 1j, and I'm going to talk through what the hypotheses are that would make you choose one of these. So here's scenario number 3, and this is I've actually started to fudge a little bit with beta 0j as well. So now let's say we have this additional question of whether sidewalks in the neighborhood presence or absence has an impact on walking in the neighborhood, and specifically whether it influences whether people walk their dogs. So what you see here is that now we have a non-randomly varying effect. So the effect of dog ownership on walking in the neighborhood depends on whether the neighborhood has sidewalks or not. And as you well know, this turns into an interaction effect. So we're asking if sidewalk presence moderates the relationship between dog ownership and walking in the neighborhood. But we hypothesize that there are no other neighborhood conditions or factors that influence that relationship. I've also added the sidewalk condition to the intercept equation, and that is obviously up to you, but it seemed reasonable to me that if I hypothesize that this has an impact on the relationship between dog ownership and walking, that there would be a general relationship between sidewalk presence or absence and walking in the neighborhood, as people might be more likely to walk with or without a dog. But as I said, this is a little bit unlikely, and we'll get back to this because if you can find one neighborhood condition, I would think in most cases you can find more than one. So here we have the fourth and last situation, and this is the situation where we have a random effect with a non-random component. So again, we're looking at beta 1j. How are we going to model beta 1j, which is the impact of dog ownership on walking in the neighborhood? And now we hypothesize that the impact of dog ownership of walking on walking depends on the presence of sidewalks and possibly other, not explicitly models neighborhood characteristics. So now we have the U1J in here again, but we also have the moderator of the sidewalk condition in this model. So as you can see, this depends on your hypotheses, and I will move on to a longitudinal example, but the structure of how I'm going to walk through this will be mirroring this first case. So if this is now crystal clear to you, you might be able to move forward a little faster. So here's example number 2, and I will be using some longitudinal data example. And this research question is inspired by Kevin Lance's research, who is looking at temperature, outside temperature and exercise that people do or don't do depending on how hot it gets. So the research question is, does walking on a given day depend on the high temperature of that day? So a possible follow-up question would be, does the relationship between temperature and walking depend on a person's fitness level? So that seems very intuitive, and the diagram on the right illustrates these hypotheses or these research questions. Here's the unconditional model, and as you might notice, this is an unconditional means model because there's not a hypothesis that there's a change over time. There's a hypothesis that there's a relationship between the high temperature of the day and the walking that happens in the neighborhood on that day. So here's the overview slide again. Notice the change in notation. We're going from betas to pi's and from u's to r's and from r's to e's. But it comes down to the same structure. We have 4 different options to model pi ti, which is the random or fixed slope associated with temperature. The effect of temperature on walking in the neighborhood. How are we going to model this? So here's the scenario if we assume that there's a fixed effect of temperature on walking. So we would just be modeling the pi ti as beta 10, and that would just be substituted in there, and there would be no random effect. So the hypothesis for this model is that the impact of temperature does not depend on individual characteristics, and that is the same as saying the impact of temperature on walking is the same across participants. So let's say the temperature increases by 10 degrees, people will walk 10 fewer minutes per week. Here we have the random effect model, where now the hypothesis is that the impact of the temperature on walking depends on individual characteristics. So that while there might be an average reduction of walking time, let's say 10 minutes per week for every 2 degrees. I was saying 10 earlier, it seemed a little bit too little. But there's an average effect, which is our beta 10, but then there's a random effect. So we assume that different people will have different reactions to increase in temperature. This scenario here is the non-randomly varying effect, and as the additional research question indicated, we would be hypothesizing that fitness level is something that we see as the moderator of the effect of temperature on walking. And in this case, we hypothesize that this is the only predictor that moderates this relationship. So we can put anything into the fitness level of a person, and there would be nothing beyond that that would have any impact of how the high temperature impacts walking in the neighborhood. Last but not least, we have now a random effect with a non-random component. So in this case, we are modeling our hypothesis that fitness moderates the relationship between temperature and walking, but we also allow for other characteristics of the person, others that we have not measured or we don't have good measurement on, or we're not able to model, or we're going to model in subsequent models. So the idea is that fitness moderates how temperature impacts walking, but there's other things that individual characteristics, individuals' inclination to walking, or something that impairs or supports their walking in the neighborhood despite higher temperatures. So this is example 3, and this is more of a traditional growth model. And the research question here is, does training seniors to walk shelter dogs increase their walking over time? The training consists of 7 weekly sessions, and this is the time variable is a week in this case. So we're looking that with more training on walking dogs, are the seniors walking more? And then there's a possible follow-up question. Does the seniors' fitness level impact the change in walking over time? So we have this program where we hope that we get people walking more, and that we hope that the better the dogs are trained and the better the seniors know how to walk with the dogs, the more they would be walking. So I'm jumping in with the growth model, and as we will discuss, model A and B are unconditional growth models. And then we will add fitness into this equation as well. So I'm going to walk again through those 4 scenarios that are a possibility, with some more realistic than others. So scenario A is one that we did not discuss in class because it is generally not a model that we see. It's a fixed effect on change over time. And the hypothesis, and this is a very strong hypothesis, is that the change over time does not depend on any individual characteristics. That means everybody changes in the same pattern over time. Let's say by increasing walking 30 more minutes every day. And so we can rephrase this for this example. The impact of the training over time does not depend on individual characteristics. It's the same across participants. But it literally means that I would expect, wherever people start doesn't matter, that with each week, everybody will walk 15 minutes more. And unless I built this in the program, I don't expect that to happen. If I build it in the program, I'm not sure what we're modeling here. So this is the unconditional growth model, and this is the standard model that builds on the hypothesis, or is built to test the hypothesis that the impact of training over time on walking depends on individual characteristics. And what it pretty much allows is for different slopes for each person, and this is what Singer and Willett model, and what we've done in class every time we've looked at change over time. So this is a traditional unconditional growth model, which is the random effects model for a change over time situation. So here is model C, which has a non-randomly varying effect, and that's the fitness effect. So the hypothesis here is that the impact of the training over time on walking depends on a person's fitness level, and it only depends on a person's fitness level. And so You can again make the argument to put this also into the pi 0 I equation, but you could also say, let's say we're starting everybody at 0. Maybe that's a condition of participating in this study, and then that would be not the right thing to do. But what I'm saying here is that there is nothing beyond fitness that I would hypothesis plays a role. Now, there are sometimes models where if we start modeling in growth models where we start modeling individual predictors where the random effect becomes non-significant, so we're kind of explaining it. I would still not suggest you running model C if we're talking about change over time. So model D is the one again that we did in class, and that's the traditional way of modeling a moderator of change over time. So we have a random effect with a non-random component, and this is, again, this is a standard way of modeling um, moderators of change over time. In our case here, again, it's fitness. So the hypothesis is that the impact of the training over time on walking depends on a person's fitness, but it might also depend on other individual characteristics. And to me and most other people who do growth curve modeling, this is just the common sense hypothesis to test. I want to close this presentation with some general thoughts. And so the first thing is if we're modeling a lower level predictor as a fixed effect, we have the strong assumption that there are no higher level factors, modeled or unmodeled, that impact the relationship of the predictor on the outcome. Now, Snyder and Boskers discuss a couple of examples or situations, and they say if the groups are regarded as a sample from a population and you want to generalize to this population of clusters, then you really should be using random slopes. So let's say we're pulling on a sample of schools or clinics or neighborhoods, and we're randomly sampling those and we want to draw general conclusions, then you need a random effect here. If you want to model group level variables, the equation where you add the variable should have a random effect. So the non-randomly varying effect is really a discouraged effect to model. So our scenario C are the ones that are most discouraged because you're saying, I have one and I know it's the only one. It's the only predictor that on the cluster level that has any impact on this relationship. So I would caution against modeling this. It would be non-traditional and you would have to have strong support for this hypothesis. Now there's one thing, and we talked about this earlier as well, random effects need a sufficient sample size on the cluster level, and the opinions vary on this. Snyder's go up to 50, sometimes up to 100, but this is based on the assumption that your random part is normally distributed with a mean of 0 and a variance of tau 0, 0, or tau 1, 1 in this case, actually. And so you can't have a distribution of just 3 clusters or 5 clusters. It even gets hard with 10 to do well on this. And so there's an issue with the modeling. So let's say you have a smaller number of clusters and you still think that you should have random effects instead of fixed one. One approach would be to test each lower level predictor as a random effect on its own and check significance and then add only those into subsequent models. I think I mentioned that I've working with Hannah Cooper, I also have seen her with small numbers of clusters, really just modeling one at a time and reporting individual models because the models just can't handle more than one random slope at a time. So this is it, and as always, please let me know if there's any questions, if I have any typos, if I made any mistakes in there, so that I can fix it. But let me know how this video is working for you. Thanks.